This video is for section 18.2 about the progress of chemical reactions. The learning goals are to understand the relationship between the specific rate constant and the speed of a reaction, and to understand how most reactions progress from start to finish. Let's take a look at that first learning goal. Understand the relationship between the value of something called the specific rate constant and the speed of the reaction. The specific rate constant is going to be represented with the letter K. The rate of a reaction depends on the concentrations of the reactants. Recall from the previous section that the greater concentration causes a faster reaction. If there's greater concentration, then there are more particles that can collide, then there will be more of the activated complexes formed, and then there can be more product formed. So with higher concentrations of reactants, a reaction will occur faster. However, as the reaction proceeds, the reactants will start to get used up. Then the reaction will slow down, because if the reactants are used up, there's not going to be as much concentration of the reactants. There will be fewer particles to collide, thus there will be less product formed. Reaction rates are not constant throughout the whole reaction. The reaction rate is proportional to the concentration of reactants, and this can be expressed with a rate law. So here in purple ink you see an example of the form of a rate law. The rate of a reaction is equal to some number times the concentration of A. The brackets around a capital letter refer to the concentration of a particular substance represented by A. So it might be the concentration of one of the reactants. A rate law is an expression that gives the rate of the reaction in terms of the concentration of the reactants. So for instance, this rate law in purple is indicating how fast a reaction is occurring based upon the concentration of reactant A, whatever that is. The letter K is the specific rate constant. It is a number. It is the multiplier needed to relate the reaction rate to the concentration of the reactants. So in the formula in purple ink, the rate of the reaction is equal to some number times the concentration of reactant A. Let's say you did an experiment and you calculated how fast the reaction is occurring when there is a particular concentration of reactant A. You could then use some algebra to discover the value of K that's needed for the equation to be a true equation. In general, the value of K will be a large number if products form quickly, and the value of K will be a small number if products form slowly. Another vocabulary word in this lesson is a first-order reaction. This is a reaction in which the rate is directly proportional to the concentration of only one reactant. For example, that rate equation that we saw on the other page. There's only one reactant given here. It's called reactant A. Notice how the exponent on reactant A is to the first power. That is a first-order reaction in substance A. Another vocabulary word is second-order reaction. This is a reaction in which the rate is proportional to the concentrations of two reactants. If we represent the two reactants using A and B instead of being specific and actually naming, certain chemicals, then here is the rate equation for a second-order reaction. It involves some number K that you'd have to figure out from doing an experiment times the concentration of the first reactant to the first power times the concentration of the second reactant also to the first power. Observe that if you add these exponents, it adds up to 2, which corresponds to the name second-order reaction. Complex reactions might have more than 2 reactants, which you could insert into a rate law expression using a C or a D or any additional letters that you need to represent each of the reactants. Rate laws can also use exponents other than 1. The rate laws that are on the screen right now in purple only go to the first power. But rate law equations could go to other exponents in order to be true equations that match what you find out experimentally. To determine the correct rate law for a reaction, it is necessary to select values of the exponents and a value for k that makes the expression fit experimentally gathered data. The next learning goal: understand how most reactions progress from start to finish. A balanced equation tells what reactants are present at the start of a reaction and what products are created by the end of the reaction. But it doesn't tell how the reaction progresses. A graph that shows all of the energy changes that occur throughout a reaction is called a reaction progress curve. Here's a vocabulary word: elementary reaction. This is a reaction in which reactants are converted to products in a single step. In the notes from the last section, we had a diagram that showed some reaction progress curves for two different reactions. I recall one of them, the final energy of the products was higher than the energy of the initial reactants. And in the other one, the final energy of the products was lower than what the reactant's energy was. Those graphs showed elementary reactions, reactions in which the reactants are converted to products with just a single step. But there are also multi-step reactions. These are reactions in which the reactants are converted to products in a series of steps. The reaction mechanism is the series of steps, or the series of elementary reactions that are involved in changing reactants to products. I see I have a typo here. That should say reactants, and that one right there should say products. An intermediate is the product of any one step in a multi-step reaction. The intermediate then becomes the reactant for the next elementary reaction. So you can think of a multi-step reaction as being a series of elementary reactions where reactants make a product, and then that product becomes reactants that then make another product, and then that product might become reactants that make yet another product, and so on until the final product is created. Here's an example reaction progress graph for the reaction of ethylene glycol with water. If you take some ethylene glycol and you mix it with water, what happens? Here are the initial reactants. This is the formula for a substance called ethylene glycol, and here is water in its ionized form, where it's picked up an additional hydrogen ion to become positively charged. When these substances react together, energy increases to form an activated complex. Some of the activated complex breaks back apart, creating the original reactants, but some of the activated complexes create a new product called a carbocation. This is an intermediate. The carbocation reacts with water to create another activated complex. Some of the activated complex breaks back apart to create the original reactants, but some of it creates a new product called a protonated alcohol. The protonated alcohol reacts with water to create an activated complex, some of which creates the final product shown down here. The main idea of the picture is simply to show that when you react ethylene glycol with water, it doesn't change into this final product in just one step. It goes through a series of elementary reactions, each one creating an intermediate that then reacts with water so that eventually this final product is formed. In a multi-step reaction, each step may occur at a different rate. The slowest step in the entire reaction is called the rate determining step. Here are some check for understanding questions. I'll pause the video for you to work on these, and then we'll take a look at the answers. Here's the answer for number 1. Reaction S has a specific rate constant K equals 2. Reaction T has the specific rate constant K equals 3. So which is faster? That's reaction T, because its K value is greater. K equals 3 is greater than K equals 2. Number 2, a reaction has the general equation A produces B, where A represents a single reactant, B represents a single product. This equation has the rate law, rate equals K times the concentration of A raised to the X power. When the initial concentration of A is increased from 0.35 to 0.70, the initial rate increases from 1.6 to 3.2. What is the order of the reaction? It is first order. Now there's different ways to do this. Informally, you could figure out its first order by noticing the direct change that happens. When the concentration doubled from 0.35 to 0.70, the rate also doubled from 1.6 to 3.2. The direct relationship between concentration and rate only goes to the first power because the changes are identical, doubling and doubling. To figure this out formally, we can use this general rate law and make substitutions of the actual experimental values. For example, our first rate, I'll call that rate number 1, is 1.6 when the value of A is 0.35. So all I've done is replace the word rate with 1.6 and replace the A with 0.35. I kept the K, I kept the X. Okay, the second time the rate was measured in an experiment, the rate was 3.2 when the value of A was 0.70. And so I made those substitutions. Now that I have these two equations, I'm going to compare them with a ratio, meaning I'm going to divide them. Now I could take rate 1 and divide by rate 2, but I've decided to take rate 2 and compare it to rate 1, because that would be taking the 3.2 on top of the 1.6. That's going to divide and make 2 instead of dividing and making a fraction. And I've taken the expressions on the right side of the equals and also compared them. Then it's time for algebra. 3.2 divided by 1.6 makes a 2. On this side, K over K cancels away. 0.70 over 0.35 just makes a 2. And notice how the exponent is x in both places, so we can write the exponent of x. This creates the very simple equation 2 equals 2 to the x power. So what does the x have to be? It has to be a 1. So we find out mathematically that the exponent is a 1. And that verifies why we said our answer was first order. Next, number 3. The rate law for the following reaction is first order in nitrogen monoxide and first order in O3, which is ozone. Write the rate law for the reaction. When it says to write a rate law, we know that we start by writing the word rate, then equals, then a K, and then we have some brackets where in the brackets are our reactants. And we know as well that there are exponents on those brackets. Because it's first order in NO, I've written NO in brackets and I've given the exponent of 1. Because it's also first order in O3, I wrote O3 in brackets and gave it the exponent of 1. This follows the basic pattern rate equals K times the concentration of A to an exponent times the concentration of B to an exponent. I'm just being specific and actually putting in the name for A and the name for B. And I'm specifically putting in the exponents that go with first order. Next, number 4. The reaction of nitrogen monoxide and oxygen has the equation 2NO plus O2 produces 2NO2. Is this reaction a single step or a multi-step reaction? I think it's multi-step. And here's the reason. In this balanced equation, we see that there are 2 molecules of this and 1 molecule of this that collide together to produce 2 molecules of this. So if 3 molecules have to collide together, remember that collision theory says those 3 molecules have to collide with sufficient energy and proper orientation that they can attach to each other to create this product. Well, it's unlikely that three molecules are going to hit into each other with just the proper orientation to make that product. It's more likely that this is multi-step, that in the first step, two of the molecules bump into each other to make an intermediate product, and then that intermediate bumps into the third molecule to end up making the final product.